Computation. It is a real pleasure to be talking to a Ukrainian audience about the problem that has been bugging me for the last 4 years or so. I'll give you a very quick introduction. As Taras was already telling you all, I come from physics, actually. I did my undergrad in physics in Spain, and then I moved to the UK. I was in Cambridge and London, Cambridge and Edinburgh. And I am trained as a mathematical physicist. I learned about general relativity and quantum field theories and all these kinds of things. So when I was doing my PhD, at some point, I was learning about Lie algebras and about the application of all this algebra to modern physics. And one of the questions that my supervisor had was, what happened if you changed the number of arguments in your algebra? So as I will tell you in a second, this was one of my motivations, but this essentially put me into a trajectory that brings me here today to tell you about hypergraphs and higher-arity algebra, which had nothing to do with my initial interests. And so the context in which I do this nowadays is twofold. So on the one hand, I am employed by the Wolfram Institute, which is an independent scientific organization funded by Stephen Wolfram. Maybe you know Mathematica and Wolfram Alpha, these kind of tools. That so the founder set up an institute a few years ago, and I am a mathematician there. We are very happy because just recently we were given a grant to fund our research for 2 more years. So I will be doing this kind of stuff for 2 more years. So maybe I can come back again in a year or two and give you the results because today I have a lot of questions, not many answers. I should say that. So yes, and the other organization is my own funded institution, which is a small association in Spain dedicated to multidisciplinary sciences. So we have physicists, mathematicians, biologists, geologists, chemists, all kinds of people coming to share different perspectives. Okay, so what about the topic today? I have one simple question that I wanted to pose back during the pandemic. I was, kind of bored. I had nothing to do at home. So I started playing around with this idea of what would be ternary associativity. So this might seem like a very childish thing to ask because you're familiar with associativity from, say, a group. You might have an operation that looks like this. Maybe call it star or something. And you want to say that for all elements, you have a property that looks like this, right? So this is extremely familiar to everyone. This is what we call associativity, nothing mysterious. So the question is, wait, so as a context, of course, groups are at the foundation of a lot of modern science, right? A lot of, both the cosmological scale and the microscopic scale has groups and Lie algebras all over the place. And of course, this axiom is everywhere, right? Like this is at the foundation of most of the mathematical structure there. So I just, for sport, I thought, what happens if I somehow, I want to define some kind of operation that takes 3 elements, some set, and send it to the set again? What kind of equation should I write here, right? That is an analog of this. So there are some obvious choices. You just bracket 3 things together and then sort of move the bracket around. So I hope to give you 2 pieces of data today that tell you that this is not a simple question. And by not a simple question, I don't mean that it's technically difficult. I don't know how technically difficult it is, but it is sort of mysterious. When I use mysterious in the title of my talk, or mysteries, is because there's something weird. It's not just mathematically difficult as in a hard problem, but it's actually difficult to think about, not only difficult to technically solve. So let me motivate that with 2 problems that are quite concrete, and but I need to give some background. So how many of you have heard of Lie algebras before in some capacity? The algebras? Okay, so I'll give a quick definition just in case. So a Lie algebra is some algebra. So you have some kind of vector space. Let me just put it here, where you send pairs to other elements in some form of bracket like this. Okay, so what defines a Lie algebra is the Jacobi identity, right? The Jacobi identity is very familiar to everyone, even though you don't call it the Jacobi identity, because it's the property of derivatives with products. When you take a derivative, something like this, of a product of 2 functions, you know what to do, right? You go derivative of the first times the second plus first times derivative of the second, right? So this expression is effectively what the Jacobi identity encapsulates, right? So what we write for a Lie algebra, apart from some antisymmetry that I'm not too concerned about, is that if you take the bracket of one element with the bracket of two other elements like this, you should see this element acting as a derivation, as a derivative on the bracket. So what you write is two terms. The first is x acting on A, so you put x acting on A, and then you bracket with B. And then the other term is the same thing, x acting on B with A. So you keep the order, x acting on B, right? So this is the Jacobi identity. This is what defines a Lie algebra. Effectively, you also want antisymmetry, but this is, some people might be familiar with the Jacobi identity when it's all on one side with cyclic permutations equal to 0. But if you just move the signs around, this is the property. So the reason why I like to see the Jacobi identity in this way, did I make a stupid mistake? No, I think that's correct. So the reason why I like to see it this way is that it is very easy to generalize for higher-arity operations. So if I have more arguments than just two, for example, 3, which is, by the way, I'm going to be dealing with ternary just because it's one step up from binary, because there's something mystical about 3. So the ternary Lie algebra, you basically just add one more factor, and now you have to take 3 arguments. And what you do is you write essentially the same equation, but now you have 3 things. So the way to think about it is very simple. So you have x, y, and then third argument. The third argument is going to be a bracket of 3 things, and let me call them A, B, and C, right? So the way I write the Jacobi identity is very simple. I just take x and y acting on A plus x and y acting on B plus x and y acting on C. So it's a bit long to write, but it's a very simple equation. So first one, x and y on A, and then we C plus A, then xy acting on B, C plus AB, and then xy acting on C, right? So this is the Jacobi identity, okay? And these algebras are quite well understood. They have been studied. There have been even applied in some contexts in physics. There is some literature that you can find about these algebras. In fact, I can give you a very natural example that you actually have worked with before, but you never called it a Lie algebra. And so this might be a bit uncomfortable to hear. It was a bit uncomfortable for me to rewire my brain a little bit. But I want to tell you about what's called the orthogonal complement algebra. So imagine that you're in a vector space, you have an inner product. And so you have a notion of orthogonality. So this is our typical Euclidean geometry, right? And now, by the way, I'm always going to be working on real dimensions, everything, anything in geometry for me is real. It's the real numbers. So imagine that you are in a Euclidean space with an inner product. So you have the notion of orthogonality. Then you know that by any collection of vectors, you can assign an orthogonal complement. You basically take the span of those, and there's a unique orthogonal complement to those vectors. And so the idea is that I want to do that construction in what we call codimension 1, right? So we take n-1 vectors in an n-dimensional space, and we take the orthogonal complement. So let's just go by dimension to see what we get with that construction. So I'll just use it here. It's not very complicated. So this is real dimension. Yes.
Your original
Right. I'm going to give you 2 problems that motivate why I should know what associativity, ternary associativity is. And this is the first one. This is about Lie algebras. So I'm making a small detour into Lie algebras to tell you about it. And then I'll give you another motivation. And hopefully you will see that there is some good reasons to think about what is ternary associativity. No, not yet. Exactly. Yeah. So far, I'm just defining Jacobi identity, which is very easy to define. This is, binary Jacobi. This is ternary Jacobi. You can do as many as you want because it's very easy to generalize. So to give you some examples of these guys, these are not just a abstract invention with no examples, to just give you some very concrete examples. Let's do this idea of defining the orthogonal complement of the codimension 1 set of vectors in any real Euclidean space. So in dimension 1, nothing happens because you have only one dimension. You don't have more dimensions to go. So effectively, that's the zero map. In dimension 2, you have 2 dimensions, so you need one vector, and you give one orthogonal complement to that vector. So what you can imagine that this is the 90-degree rotation on the plane, right? So if you are a geometer, the way you think about this is you call this the complex structure of the plane, right? Because you are effectively multiplying by I in the complex numbers, right? So, but if you are a high school student and you're just learning about basis vectors and determinants, you might want to write this operation as, the basis vectors E1, E2, and then your components X1, X2, right? If you take this determinant and you multiply it out, you get X2 minus X1, which corresponds to 90-degree rotation of your axis. Okay. What happens when I do it in 3 dimensions? Well, I just write the same formula, but with 3 things. And everyone knows what this is, right? Oops. This is just the SO3 Lie algebra. This is the Lie algebra of rotations in space. So a proper Lie algebra, a Lie algebra of this kind, a binary Lie algebra, right? This is the cross product. Everyone knows about the cross product. Okay, but I can keep going, right? Nothing stops me from just writing 4, 5, etc. I just need to go to 4 over here. I won't write everything, right? But you can imagine what I would write. So some x, some y, and some z vectors, right? And you have exactly the same construction that gives you an algebra of this kind. It's a very tedious thing to prove because it's very long, but you get the exact same axiom here. And in fact, if you keep going 5 and 6 and so on, you're always getting at dimension m, you get an n-1-ary Lie algebra with this construction, right? So it is a very simple construction. It is, we all work with 4-dimensional metric spaces. This is space-time. 4-dimensional Euclidean geometry is extremely common. Probably you never thought of it as having a ternary Lie algebra structure. No one thinks of it in that way. It's kind of weird. But anyway, it's there. It's simple. And so, okay, so we have some examples of these guys. And the main story about Lie algebras, if you've seen it before, is that they are the infinitesimal component of a Lie group, right? So without any details, what I want you to remember from this is that if I give you a Lie algebra, actually, if I give you a Lie group, yes.
So this is just the ternary operation on linear vector space.
Yes. The bracket, that's the bracket. This is the bracket. This is the bracket of x, y, z. This is the definition of the bracket. Just the same like this is x sort of cross y vector product. This is the bracket itself. So, I mean, I would write x1, x2, x3, but just not to write, it's just the 3 vectors over there. No. This is all the algebra. This is only algebra. Yeah. So this is, no. This is the algebra operation. And this algebra satisfies this axiom. Very long to prove, but trivial. And actually, if you keep going, they keep satisfying the corresponding axioms all the way. An interesting anecdote is that this is really the complex numbers when seen as a vector space over the reals. So a funny thing to maybe know from now on is that the Jacobi identity for unary operations is the property of the complex numbers. The minus idempotence, right? The x squared equals minus 1 is kind of Jacobi identity for unary operations. But anyway, that's just a funny side thing. Okay, so what is important is that whenever we have a Lie algebra, like this one, a conventional binary Lie algebra. So I'll put it here like this. We can actually find a group G with a manifold structure, so that when we take the tangent space at the identity of the group, these things are actually isomorphic as Lie algebras. So you can think of these as the left invariant vector fields or the vectors transported to the identity. You can see it in several ways, but basically you take a geometric structure on a global group that has a manifold structure, look at the identity, what's happening there with infinitesimal transformations, which are small deviations from the identity, and the group operation turns into a Lie algebra operation, right? So here what we have is an associative product, right? This is an associative operation. I mean, it is more things than associative. It has an inverse, it has an identity and so on, but at least one of the algebraic features is that it is associative. And here we have Lie algebra, right? And so this is the central result of Lie theory, right? That you can go back and forth, and especially if I just give you a Lie group, it is immediate. It's a direct construction to find its Lie algebra, right? So at least in some simplified story, if you give me a Lie group, I will immediately calculate a unique Lie algebra on the tangent. So the question I pose is, what kind of object should I give you so that when I do something infinitesimal to it, you get this kind of guy, or generally this kind of guy, right? So that is the first open problem. It is actually an open problem. Yes. You mean, yes, so this one, yes, so the binary one, exactly. So yes, so the story is a bit more sophisticated than just saying associativity, but for the sake of presentation, I will restrict to the case where this is true. This is not strictly the most general thing, but in sufficient generality for the argument, the thing that you have to use to show that this is true for when you construct your, so here you have vector fields and you always have some commutator of vector fields. In order to show that vector fields close, left invariant vector fields close under commutator, which effectively tells you that they form a Lie algebra, finite dimensional Lie algebra, you have to use associativity of the group operation. That is, it's a crucial step to get there. So the expectation is that, if we found some kind of ternary group that had something like a ternary operation that is associative, maybe we can infinitesimally find something that satisfies that. No one knows. It's still an open question. Not many people have tried, but it is a valid mathematical open question. It's just there, sitting to be solved. All right, so this is one angle from the theory of Lie algebras. So if you've never heard of Lie algebras, this might be a little bit distant. You might be a bit skeptical. It's like, is that just a technicality? So we'll give you another open problem that I think is much more tangible, that I think anyone can follow, which is hypermatrix multiplications. So this is the game of generalizing matrix multiplication. So if this was kind of high school mathematics, this sort of cross product formula with a determinant, we're going even back, further back in high school mathematics to talk about this. So imagine that you're back in high school, or whenever to some of my students, I say when you were in kindergarten learning about matrices for the first time. Imagine that you're learning about matrices for the first time. And of course, a matrix is not a linear operation in the category of vectors. That's very advanced. For you, a matrix is just an array of numbers, right? So a matrix for me, is some box of numbers. I have I, j, k. Let's assume square matrices over the reals, again, just for concreteness. So when you give me objects of this kind, you say, well, how can you define an operation between this objects that is closed and has some interesting algebraic behavior? You can play around. You say, well, we can do point-wise operations like addition, right? Every element added with every other element of the same index, and so on. But then you realize that there's a combination. There are not many options because the combinatorics isn't that big. But one of the combinations is particularly nice because it is associative and generally non-commutative and so on. So we have the typical formula for matrix multiplication, right? So I say A P times B P J, right? Something like this. This is totally elementary. How should I be giving a seminar to mathematicians writing this formula in the blackboard? That's a bit funny. But the point I want to make is that, okay, imagine that I want to deal with 3 index arrays, right? So this some people say, oh, you're talking about tensors. No, I'm not talking about tensors. I'm talking about 3 index arrays. I don't even know linear algebra. I don't even know what a covariant or contravariant index is or anything like that. So just take 3 indexed arrays and now try to play the same game. What are the possible operations that you can define with 3 index arrays that maybe have some interesting property, but most importantly, that they are closed, right? They're well defined and closed. By closed means that, here I begin with 2 objects which are square arrays, and I end up with a square array. But it's non-trivial, right? Because you could do random things to the indices, but you might end up with things that are just vectors or just scalars or bigger index. Like you could, for example, do the kind of tensor product KL, something like that. That is a valid product of matrices, but it's now a 4-index object, right? So to do an operation, meaning something that sends several kinds of objects to the same kind of object, I had to do some adjusting of indices to have it working. Okay, so the question is, can I do that for 3 index objects, like I did for so this is, by the way, what we're calling hypermatrices. If this is a matrix, we call things with more indices hypermatrices, just for the analogy with hypergraphs that I maybe tell you about a bit later. So it turns out, so I have a paper on this. I can give you the reference later, where we do the exploration on what are the possible products that can be defined. I'm not the first person to look into this. I think the first people defining operations on hypermatrices were in the 80s, 1980s, late 1980s, early 1990s. So it's a relatively recent thing. Not many papers have been written about it, but there's some literature. And I'll just give you a couple of possibilities. So one possibility is to do the following. If you don't consider the combinatorics of ordering, there are about 10 different possibilities that you can do. So if what you want is an operation that takes some number of 3-index arrays and gives you a 3-index array, there are about 10 possible. I'll just give you a couple for a good illustration. So one of them is the following, which in my view and in many other mathematicians' point of view, I'll just write together like that. I have 3 ABC 3-index objects. It's a new 3-index object. And the way I define it, it mirrors very closely this formula. So I have one single summed over index, P. So what I'm going to do is I'm going to multiply the 3 matrices like that, and I'm going to try and mirror as closely as possible this formula. So what I would do is I would keep 2 indices of the first argument free, and then sum over the third, and so on, right? I sum over the second and leave the others free, and sum over the first and leave these ones free, right? So this is a possibility. This is actually an operation that you can find in the literature, 1990. So that's Acharya Messner. I'm giving you a reference because there are almost no references that I can give you in this topic, but this one operation is actually being described before in the year 1990, and it is trying to generalize matrix multiplication as closely as possible just by having more arguments, right? By the way, you could define some binary operations where you're asymmetrically combining the indices so that you end up with 3 indices, but the only the first example of a symmetric sort of egalitarian, so to speak, operation that treats every argument the same with every index the same is this one example. This is one possibility. Another possibility that we call the fish for reasons that will become apparent in a bit is the following. So this one has 3 summed index, so P, Q, and R, and it looks something like this. So I take, PQ here, B goes into, what is this? R, PQ here, times C, and this is, just PQ, PQ, and this is R here and JK, right? So this is another possibility. You see it's already a lot less symmetrical than the other one because, here I'm summing 2, here I'm summing 1. It has the 3 matrices enter the product in asymmetrical rows. but it's another possibility, right? And as I said, if you go through the combinatorics up to symmetries of reordering, there are about 10 possibilities that you could do. Okay, so this is just laying the groundwork for the question. So the question is, this guy here satisfies a very nice property, right? If I give you matrices and I tell you to multiply them like that, this is true, right? It's an associative product. That's what we know about a matrix multiplication. So what about this guy? What kind of associativity property or what kind of equational identity does this guy satisfy? Well, it turns out that, well, first of all, when you search, for example, with a computer search program, you find nothing. You start by checking how many 5-element expressions. So you could check things like this. Is this true? Right? The obvious associativity property, right? Is this equal to, for example, move the bracket, right? Something like this. E, C, D, E. Right? This is a reasonable thing to ask, right? This one could think that this is ternary associativity, where I can just move the brackets to the next, which is exactly the property you get when you take two associative binary operations and you put them together, right? You get that. Is this the case? No, this is not the case. Is it the case that, I don't know, I can change maybe B now goes like that? I don't know, I get B over here, I get D over here, and I get C over here, for example. Is this the case? No, that's not the case. So you try all the possible axioms involving 5 elements, 7 elements, 9 elements, you find nothing. It's not that you find something weird, it's that you find nothing. Right, we tried everything. You can repeat letters, you try all possible equational identities, you find nothing. So this is very disconcerting. I mean, I'm talking about this one specifically when I say you find nothing. This is a bit disconcerting because somehow we just defined a matrix operation that's very similar to this one. And these are numbers, right? These are
select this next, right? This matrix just this line.
this one, yes. Or linear maps, yes. It's of course associative, yes. Wonderful question. We don't know. So, so that's a wonderful question that I have wondered for the last 3 years. We don't have an answer for that. My hunch is that, I mean, the direct analogy would be to say that these things are ternary linear relations, because in a way they are. If you set up a 3 vector spaces and you define a subspace of the Cartesian product, where every time you have 3 arguments enter into a trilinear form, you know, when equals 0 or equals some value, then it's true, then that's a linear relation, right? So that is one possible interpretation, that these things are linear relations, and this is one way of composing linear relations. So however interpretation, because that's part of the philosophy here involved, like how do these things work, there is a more basic question to be asking here, which is, if I just define these things as I did, right? These are numbers over the reals or over your favorite semi-group, semi-ring, your favorite semi-ring, whatever you want. I can write this equation now. This defines a ternary operation in my set. How does it behave? What kind of algebra is it? So far, the typical methods will tell you that this is a magma that doesn't have any particular axiomatic properties, which to me is very confusing or very unexpected, because it is extremely well grounded in operations that are very rigid. These are associative, commutative, distributive operations, right? Has a lot of sort of fundamental algebraic richness already. So that was one first surprise. This thing has no axioms. Now, this one, when you search, you find the following axiom. Actually, I think I wrote it here already. So you find, for this one now, for what I call the fish, you actually find that this is true, that you put this one here, and you swap B and B, and then this is in turn equal to moving all the way to the right, C, D, E. So actually, this actually works for this one. This guy over here has this, and this is what it's called a semi-heap, whatever, it has some name. people wrote about this stuff. They actually defined these objects at some point. So this does have something that is very close to associativity, as in these two look like associativity. This one here is just swapping D and C from the linear order. Okay, so what allowed me to say that this thing was going to have an axiom and this thing will not have an axiom? And how can I find the axioms, or how can I prove there are no axioms, right? So this is the open problem number 2. I have 3 index arrays. There are very natural definitions of operations. What are the axioms, right? So, yes. Yes, this is a good point. If you could, for example, if I understand correctly, assume that your matrices are all symmetric or having some conditions on them, something like that. We have tried. We haven't found anything very interesting. Maybe we didn't try well enough for or sufficiently clever choices of subsets of matrices. But there's quite a lot of literature. I recommend that you search for, if you're curious, you can see in my papers, I have a collection of references for people who have studied this thing quite heavily. They have found a lot of structure here. It's not that there's no structure whatsoever. They have found a lot of structure, for example, in there are certain facts, like if you use this as a binary operation by fixing an element, the thing becomes associative under some conditions. There's some structure there, but the more naive, almost childlike question is to ask, well, if this thing has that axiom, what axiom has this thing that is directly generalizing it? And that question is open. It's not that there are no axioms, it's that we don't know if there are axioms, and that is quite uncomfortable. So I have a summary of these things here. I think because I use the Blackboard, it's well enough for you to look at here. But the point that I want to do with this slide is just to show you how I came into hypergraphs. So let me maybe go back to the top, which should explain what I'm doing here. Over there, I have what I explained here. So some indices might be too small, so don't worry too much. You can look at the Blackboard. But the point was to try and represent the index contraction patterns, so the I with the J and the P in the middle and so on, as a diagram here, right, with a graph. So all you do is you say, well, what are my 3 indices, I and J? What is my contracted index, P? And then you draw a line whenever you have a matrix, right? So this line over here corresponds to the matrix, and that line over here corresponds to a matrix. So similarly, you could define, something like that, where now you have 3 matrices, and this is a quite atypical product because you are summing 1, 2, and 3, and you get something that is no longer a matrix. You get something within 3 indices, I, J, and K. And okay, that's something you can do. It's no longer an actual operation because it goes into some other set. But then you can do the thing that I just did here, the so-called Bhattacharya-Messner operation. And so if you want to represent in the same fashion, where you're taking inspiration maybe from category theory, perhaps, or graph theory, where you're representing your matrices as edges on a graph where the nodes are the indices, then these 3 index objects should be represented as little triangles. Or if you're in the context of graph theory, you should call them hyper edges, right? So the diagram should be a hypergraph and not just a graph. I like these diagrams. I started using them just to keep a track of what I'm doing. Obviously, if you look at this formula or this formula over here, it looks complicated, right? You have to read a bit, okay, it's kind of like messy. But if you look at this, it's okay, that's a nice little symbol, 3 triangles in this kind of tetrahedron configuration. It's easy to remember, easy to see. So we use these to basically classify the possible operations. And the reason I call this the fish is because when you represent the indices, it looks like a fish. I mean, there's nothing very very mysterious about this. It's just it looks like a fish, we call it a fish. So if you represent each matrix like a triangle, you put your 3 indices where they should be free, sort of not in contact with anything else, and you put the ones that are in contact, that are summed over adjacent in a hypergraph, you get this fish structure. Okay. So as I said, the summary here is that the binary operation is associative. the fish operation is a semi-heap. So it has this particular equation being satisfied, but specifically the one that's called the Zapata-Carratalá has no known property. That is one of the problems. All right. So these two problems, especially the second one, this one, was what motivated me to go into this direction of, okay, what is the right approach? What is the right approach to associativity? So I'm not just naively asking what is ternary associativity, but I am more generally thinking, how should I understand associativity? Because it seemed to me that I was kind of stuck. Like I was making no progress. This was very intractable. Computers were not finding anything. I was talking to several mathematicians that had experience in these fields because I didn't. This was a curiosity for me. And they were telling me, this is helpless. We don't know anything. In fact, I got some emails from mathematicians around the world saying, "Oh yeah, when I was in my early 20s, I was very hopeful and I did some research on this, but then I dropped it." And so I actually got like a few anecdotes of people that went into these things and then got burnt out and never revisited it again. So it was a bit uncomfortable for me. I was like, okay, I need to rethink what associativity should be. So this is mostly what I think my contribution has been in the last few years, and what I hope to put forward in the next 2 years of grant research. So my idea was to take inspiration from the composition of morphisms in category theory, and try and have a better understanding. So what should I think? So the idea is, in fact, I might just show you okay, I'll do the morphisms on the blackboard, and then that should give you the idea. So how many of you have seen the definition of a category before? Okay, so in category theory, you have, you can define it in several ways, but you can define diagrammatic calculus that looks at things that we call objects, which are your sort of basic elements, and sort of relations between them that we call morphisms, right? And when you find something like this, you could call this morphism F and this one G, you say, if I can go from A to B with morphism F and B to C with morphism G, then I can go from A to C with morphism something else that is the composition of those two. So what I wanted to do is, okay, let's imagine that this is a rule that you apply in your diagrammatic rewriting. So imagine this is a pattern matching machine, right? Like in computer science, you have a lot of sort of pattern matching algorithms where you're just fanning for a specific pattern and then you act a change when you find that pattern. So I thought of categorical composition as a kind of pattern matching machine, or as we now call it, a rewriting rule. So a rewriting rule basically needs an input context where you say, this is what I want to search for when I find this pattern. I'm going to transform that context into something new. So we are going to leave the objects as they are, and we are going to create a new edge that is somehow dependent on these two edges. So I will put a morphism over here, and I will give it a name, maybe something like that, that has that evokes the name of f and g. So, okay, so I take, in fact, I'll just draw this notation. I'll just write it like this with a bracket, which is shorter and cleaner. Okay, so when you first learn about associativity in categories, you normally are given a first explanation with a diagram that has now 3 morphisms instead of 2. So I think, where's the best place to do this? Yeah, I'll just write here and then I'll extend the diagram this way. So if I give you this diagram, and I'm going to omit the names of the objects because I'll just draw them on the blackboard and you can keep track of them. So let's call them FGH, the morphisms. And I tell you, okay, do pattern matching with this rule on this diagram. You say, well, there's 2 matches, right? There's a FG match over here, and there is a GH match over here. So the whole idea of rewriting theory is that you apply the matches everywhere you can. And then you follow the histories that follow from each of these applications. So let's follow the history of the first match over here. So that history is the one that takes these two and turns into one. So I'll have something like that. So this one now it's called FG, and this is H. And the other path in the history here is doing the other thing. So there's F over here, and then there is GH over here, right? And there's another object over there. Okay, now the idea of rewriting theory is that you follow, again, all the possible applications. So you look at the possible matches here. Okay, so there's one between this and that. And you look at here, and there's one between this and that. So we actually end up with a diagram that looks the same for both cases. So it has the same four objects as in the beginning, but one is a single arrow from here called F, G, and then H. And the other is an arrow that is called, well, first GH and then F, right? So the associativity axiom of categories amounts to saying, actually, you don't have two arrows, you have one arrow. It amounts to saying these two things are equal, right? You need the two arrows to be the same. So, I mean, this is a standard first page of a category theory textbooks. This is super basic stuff. But I was very inspired by this logic, and I wanted to basically promote this almost pedagogical tool to something that was more like a machine, a mathematical tool to be able to understand associativity. Because this, to me, this was somehow capturing associativity, right? The fact that you give me a diagram, I follow two paths, and I arrive to something that there's some kind of ambiguity where I should be calling, there's an ambiguity of what name I should give to the same arrow, right? Somehow that was capturing associativity. So I said, can I find this in some other situation? And so the big surprise was that, yes, we actually found it with my colleague. We found a result for the fish diagram. So instead of drawing on the blackboard, because it's going to take me a long time, I'm actually going to show you a little notebook that has this example. I'll try not to spoil it too much. All right, so I hope that this is sufficiently visible. I'll make it bigger. Forget about the code. Just look at the... So this is actually... Oh, the contrast is very low. Huh. Give me a sec. No. So I might just change. Let's see. It's not much better. Maybe if I... Yes. Can you see the shape more or less? Right. So, I mean, just for reference, I'll show you the one above. This is the shape that I just drew, right? I mean, yeah. So I have two arrows goes to one arrow, and then I have three arrows like here. And so I have this diagram where I have two different paths, and I go to a single place. And then there's this analysis that there was some overlap that I'll tell you about in a second. But for now, so this is actually Mathematica. So this is the software this is the reason why I joined Wolfram, because I was doing this by hand effectively. And since I joined, we actually worked on developing. So I am developing this with my colleagues. The language is Mathematica, but the Packlet is something that we've developed over the last couple of years. So the pattern here is you take, again, the nodes are like objects in a category, but we don't know what they are. They are just graphs for now. And you label X, Y, and Z, the parts of the fish. So actually this is tail, body, and head. And that's why you put X, Y, and Z in that order. First argument is tail, second argument is body, third argument is head. So there's kind of a topological way of assigning the positions. And then what you do is you take this particular diagram, this long fish, which has, A, B, C, D, E, 5 arguments, right? Remember, we wanted to get to something like this axiom that had 5 elements, so it should be something with 5 things. And now what we do is we apply the rule, this fish rule that turns the fish into a triangle between the tips of the tail and the mouth, right, into this diagram. So just without looking at the next bit of the slide, you can probably already see that there are some obvious matches, right? You can see there's a fish over here. I'll get the pointer. There's a fish over here. There's a fish over here. But very crucially, there is a fish swimming in the opposite direction in the middle. So that's where the clever trick is. And that was the discovery. I mean, it's very childish, but it's very satisfying when you found it. So, I mean, this is our software that does the actual rewriting in the background. So you can barely see. This is unfortunate. But here you can see that the triangle on the leftmost side was rewritten to ABC, right? Because those were the three triangles over here, right? A, B, and C on the left are there. And then the one in the middle corresponds to the left rewriting, and then the one over there corresponds to the middle rewriting. And so each of these are independent. These intermediate terms are independent, but then they all rewrite. These all look like fish. That's the point. 1, 2, and 3, they all look like fish. So they are going to be rewritten to a single triangle. And that single triangle, it's going to have 3 different names. I mean, you can really see, maybe if I change back to light, you can see better. Yeah, this is much clearer. So maybe you can see that here in each step, you get ABC here, you get CDE here, and you get DCB over here. And so you rewrite all of them because they are fish. They are the same shape. And you get, in all 3 cases, a triangle between the same vertices, 1, 9, and 2, labeled like that. Just like in here, we got 2 arrows between the same 2 vertices. And it just so happens that they have 3 different names. By the way we label things, they have 3 different names. Those names are exactly the axioms that I had in the presentation slide, right? So when I went here, those axioms, right? Exactly this equation over here corresponds to the 3 different names that one finds when you go through the fish rewriting. So this to us was a pretty big discovery. I mean, at least to me at the time, I didn't know what to make with it because it was just a kind of a curiosity. It's like, okay, we didn't know why the matrices, when you multiply it in this way, satisfy this axiom. They just do. It's just something that's a true statement. But now we had a pretty solid argument that what happens in categories, which is normally only used as a pedagogical tool to show students how you should manipulate commutative diagrams, actually can be promoted to a criterion to detect associativity, because by the exact same token, we found the associativity of semi-heaps, which in principle has nothing to do with associativity of binary operations, because this is, it doesn't have any binary operation inside. And without knowing anything about that, we were able to find the axiom independently. So at first, we thought that this was a new algebra. And then we actually went into the literature and found that, oh, no, actually, this was defined as a semi-heap, and there's some history to it. So we got quite optimistic to be able to say, well, this criterion tells us what associativity should be. So we have an entire program that is about to start. And that's why I'm here today to tell you, we have questions and we have initial evidence, but we don't have the answers. And so basically, I guess the conclusion that I can give you is, a couple of research goals out of this. So the first one is now that we have a system that allow me to define operations in terms of rewrite rules, all you have to do is enumerate the possibilities. So you have a finite number of elements involved in the right-hand side, in the left-hand side. You have a finite number of elements involved in the right-hand side. So you can just extensively enumerate what happens when you have one element into one element, two, and all possible combinations into one into all possible combinations of two, and so on, right? So you do some basic combinatorics to enumerate all possible graphs and hypergraphs that look like operations, which, you know, there's some conditions that you have to impose, but it's very straightforward. And so you can indeed search for all possible initial conditions. So what kind of diagrams you will begin with to rewrite and see if you get something. And up to a certain size, we can claim this is all the possible algebras that can be found in this way. Hopefully, within those, and not very far into the high-arity territory, we find some things that have associativity like we expect, that can actually be used to solve the problems that we had in the beginning. So the second one, which is connected to what I'm saying, is that we want to characterize the non-equational properties of those algebras. So I just told you a couple of slides ago, like these things seems quite mysterious that some of them will have some equational property and some of them won't have any equational property. And the thing is, you can define, as I said, up to 10 different operations of this kind. Of all 10, the only one that has some property is this one, at least so far, as far as we know. And so what is very interesting, and you know, that's why I say in the slide that this might be effectively establishing a new branch of mathematics. It sounds very grandiose, but what this means is simply that algebra as a conventional discipline, and more specifically universal algebra and sort of categorical algebra as it is done nowadays, would look at these different possibilities that you can define with diagrams and with different shufflings of the indices, and they will tell you, this is a ternary magma, 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 because they have no equational identities. So algebra will tell you, I can distinguish between them, because algebraically they are the same non-species. They just have ternary operations with no additional structure. But it is very obvious that they are different, because in fact you can prove that they are non-isomorphic, because they're just there sitting finitely many elements. You can generate them and show that at least for some models of those algebras, they are non-isomorphic. And you know that they are somehow genetically different because they are made of different operations, right? Like the pattern that you are using to define the operations is different. So there's a possibility here that we might be unveiling a new kind of analysis tool that is finer than algebra, because it allows you to somehow look under the hood of some of these operations that algebra just sees as magmas, because they are just magmas. I mean, it seems that no, by the way, one of my colleagues in Colorado, in the University of Colorado Boulder, has a proof that the Zapata-Carratalá product, so this one, so the proof we still have to confirm and so on, but it looks complete. He has a proof that this thing actually has no axioms. So it's not that we don't know, but it follows no, by axioms I mean no equational identities. So that first search that we did with a computer up to, I think, 7 elements, which was millions and millions of checks, it came out empty. It's actually a feature of the whole thing. Doesn't matter how high you try to find an axiom, like with 2,000 elements combined in very complicated ways, nothing is going to be true. No equation of some combination of elements in brackets is going to be equal to some other combination of elements in brackets. So that to me is a very unique opportunity for a mathematical scientist like myself, because that basically tells me that on the one hand, there's a very obvious thing that is kind of transparent to modern mathematics, which is this algebras defined from hypermatrices that just don't have any properties that are seen by traditional methods. And on the other hand, we have methods that can discern between them, because we can, define clearly when one algebra is one kind or another kind. We know if we have a fish, or we have a triangle of triangles, or we have something else. This we can identify very clearly. And the fact that it's fully computational, the fact that we can run our algorithms and search and say definitively this thing is convergent and confluent in these terms, and therefore this might be an equation here or not. We have that ability to study these objects without having to use some theory that is basically saying, I can tell you more than they are magmas. And then final goal, of course, is, as I began my talk, is to feed back into the open problems in higher-arity algebra. I mean, I am currently far from answering the questions that I began with. So that's why I warned you. I come with a lot of questions and not a lot of answers. I ended up in this territory because I felt it was the most productive. I couldn't find a better way. I talked to very good category theorists in Edinburgh. I talked to algebraists. I talked to geometers. I mean, I am a geometer by training. I was in contact with, in forums, in international conferences. I've talked to a lot of people in the international community. The average response to this problem is, that's interesting, but I have no idea. So it's never been dismissed as something that is useless, but it's always been kind of uncomfortable because you think about this problem for about 5 minutes and you get confused because it's very deceitfully simple, but at the same time very hard to make any progress on. So yeah, that is the questions that I've been thinking about, and yeah, I'm very happy to continue discussing. But thanks for your attention. Is that in order to the product that we are looking into the most, which is this Zapata-Carratalá business, just to put the formula on the screen. Yeah, this guy over here. If you represent it with a tensor network, you would have to represent something like this. So you have one identity in the middle, and you need 3 wires, and then you have 3 things. So let's see. One triangle over here. Okay, let me just draw one triangle like that, one triangle like that, and one triangle like that. And then over here, it's a product that is not quite, this is like a Hadamard product that happens in pairs of indices. And so when I was showing this to my colleagues that knew some, I'm not an expert on tensor networks, but when I was showing this kind of structure, they were saying, well, okay, that's it. Like it's there. And like the question was, how can you combine this with other triangles over here that have, that can compose and form sort of reductive structures? It was uncomfortable for them for 2 reasons. First, because it's not very common that you do this in 3-way wires, because this is, in some sense, this is at the crux of why this is difficult, I would say. This thing over here is basically delta ijk, right? It's the identity of 3 indices, right? It's kind of a tensor with 1s in the diagonal and 0s everywhere else. And so you're contracting your 3 tensors, right, with one single identity tensor, each of them pairwise. So it's a conventional. So you can, what I mean is that you can put a delta ijk over here that actually is, the P, if you put a delta PRQ, and these are PRQ indices, that's the same equation, right? And so the problem was that then all the weight of the operation falls under this guy, right? Like this guy is basically giving the structure to the operation. And funnily enough, this guy over here looks very mundane. Every physicist use this symbol at some point. When you try to understand what this is from a multilinear algebra point of view, this is kind of weird. This is, I mean, in some sense it's obvious, but the question of how do you interpret your morphisms comes back to this: is what is a ternary Kronecker delta? Well, it's some kind of 3 form, right? It's a non-degenerate trilinear form. That much we can say. But the thing is, it is the ternary generalization of the dot product, for example, right? So in the same way that the dot product in 2 dimensions, or sorry, in the binary sense, defines geometry, Euclidean local geometry and things like that, this thing defines very complicated things that are not like geometry, because this is no longer positive definite, and there's some problems. So all I'm trying to say is that when you use tensor networks, the reasons why these things are difficult is because you find these three-way wires. Everything else is fine. Everything else, tensor networks, I'm pretty sure that they will be able to tell you, like, for example, the fish, just to tell you that, tensor networks makes a lot of sense. Like the fish, you can very easily see like this, right? In a tensor network way, right? This is the fish. Each connection over here, it's a conventional index contraction in the usual sense. And in fact, if this is A, B, C, you can actually group you can group your tensors by saying I have two indices and one index and two indices. You can group the indices, and this operation effectively corresponds to this operation. Like if you group the indices, you just look at the indices over there, and you can see that they are in blocks, right? I contract P is one block and IJ is another block, and they work like that. It's effectively, this is the operation that you're doing there, and so then you can understand why it's associative, almost associative, because this is actually a binary operation that is just happening next to another, and the twist in the middle, the C and B are flipped because of the transpose that flips. So tensor networks absolutely are relevant here, and they encode all these things. But if you look at this problem from the point of view of tensor networks, the weirdness gets shuffled to a point where when you look into the products that are mysterious, the ones that are these ternary things, like this. In fact, in my PhD thesis, I think at one point, I characterized modern differential geometry as all for geometry, but without geometry. As all for geometry, but without geometry. Because we do all kinds of abstract algebra, category theory, and all this, but we never actually did any geometry. But anyway, the example that I had in mind has to do with knots, right? So as I was telling you in our lunch or in our coffee, there are the Borromean links. This example is, I'm sure everyone is aware, has a very fundamental ternary property to it, which is if you take any pair of links in the structure, they are unlinked. But if you consider the set of all three together, they are bound, right? This is the Borromean. Maybe I can just. I think I have. If I remember, I don't need the internet. I just need. What was this? Maybe I don't have it here. Oh, actually, is it here? It might be at the top. A sec. No, I don't have it here. But does everyone know about the Borromean rings? Has someone doesn't know about the Borromean rings? Okay, so the Borromean rings are three rings in space that you can have two rings that are linked like that, right? So something like that, right? They are linked, pairwise linked. Or I mean, and I could add a third one that is linked to both of them, right? Like something like that. This is on top, this is on the bottom, this is at the bottom, that's on top, right? So these are all linked together. So if I cut one open, the other two are still linked. But the Borromean rings are such that, so they're easy to draw. If you draw it like this, you put one like that, right? And then the third one that goes sort of in the perpendicular direction in here. So it's not very easy to see, but like that. So in a way, if as you can see, I can slide any pair of them open, but all three are bound together, right? And this is very easy with three pieces of rope. You can just build it. So it's a well-known link. So it's a three-ring link, and so it has that property that the pairwise connection is non-existent. There's no connectivity at binary level, but at ternary level there's a bound, right? And what's important is that there can be pairwise connection, right? You could have something like this kind of link between any two of them, and you can in fact like add it, and the topology is different, right? So there's a very clear topological motivation where you could say, okay, I have a link system. So I have many such rings in space. There are some embeddings of the circle in 3 dimensions. And I want to operate the links based on their topology, right? So one natural question would be to say, well, how do I deal with, imagine that, these are very complicated things. So one is like that, the other is like that, there's another like that, there's a complicated ring system in space, and you want to make sort of topological operations. You want to say, okay, whenever there's a Borromean link, I'm going to merge all 3 into a single joint and keep the process. The question is, can you do that consistently? If does it depend on the order, for example? That is one question. And so the kind of operation that you're defining is a set of all elements that have a ternary operation, which is if they are found in a Borromean link, mix them or make some surgery to them or something like that. And that set becomes your algebra, and that algebra has naturally a ternary operation. So the real question is, can you find these possible algebras that we found in those algebras, and then can you define the operations that will predict whether they are Borromean topology or only pairwise topology, or these kinds of things. Yes. You can see it at the level of, I don't think it's the fundamental group itself, but in the cohomology of the complement, you can characterize the, I forget now the construction, but when I was in Edinburgh, my topologist colleagues were telling me about this particular. So there's an invariant of the complement that vanishes when there's no Borromean structure, and it's non-zero when there's Borromean structure. So you can geometrically fully characterize. That's the part that no one could tell me, because for example, there is a vector calculus way to compute the same way that you can compute sort of winding number with some formula, right? And if you use the embeddings, you can do an integral formula to basically compute the linkage. There is an integral formula to compute the Borromeanity of 3 links, but it looks very complicated. When you look at the calculation, it looks like many cross products and dot products, and some people do it over quaternions because it's easier. So it doesn't look clean at all. This other formula is super clean. It's just pretty much it's just take the cross product between the radii between the legs. It's very simple. The Borromean one is very complicated. So my suspicion is that if you have a good understanding of this guy, which is the 3-dimensional, the ternary version of the pairing, so it's a triple conjugation of vectors, and the associated geometry to it. So in the same way that, so the associated geometry is like the ternary Lie algebra that I described earlier with 3 arguments and so on. If you had a good understanding of that, you could formulate something like Borromeanity in a very compact way. But yeah, right. There could be something in that direction, yes. I have to say I have not worked a lot on the topology side because I was mostly dealing with the algebra and the matrices and all these things. But my feeling I would say is quite evidence-based, but after a lot of evidence, this guy seems to be the barrier. Like, just to give you a sense, when you do planar geometry, Euclidean planar geometry, and you define distance for the first time, the first thing that comes out is the conic sections, right? Like your curves for where you are defining something about distance is the conics, right? So the topology of the conics are very simple, right? You are basically like a circle topology or like a line topology. There's nothing else. Maybe a cross topology in one degenerate case. When you look at this product, which is basically taking, dot product with 3 elements, it's nothing super fancy. Your conic sections, now it's sort of cubics, right? It's some cubic equations. If you look at just in the plane, what are the possible topologies of the conics, of the cubics, sorry, it's quite complicated. It suddenly becomes, you have a circle and a line, you have a circle crossed by a line, you have... Well, I mean, this is just to make the definition of the dot product, right? So if you begin, when you do the dot product, like in 2 dimensions, you do something like this, right? Right? So you can just do whatever x, y, z, something like that. So you just write the same thing, but with 3 elements. If you just, that's the cubic. That's what I mean. It's cubic, and this thing is basically delta ijk, right? It's sort of I plug x, y, and z to the tensor, right? But now I have 3 types of indices, and there's a whole story here about the generalization of covariant and contravariant, which there should be something like, again, the generalization of duality. There's now this triality, which is a different thing that is not very well understood, not basically anything written about it. And so if you just for a sense, the kind of curves that you get here in the plane, these are the conic sections. The kind of curves that you get here, these are the cubics in the plane, but these are topologically quite complicated already. So
this unsolvable, like in algebra equations and like the power of being can be done with different situations.
yes,
Or just
probably not. But I think the mystery remains to me that in the case of 3, it looks totally tractable, but somehow the objects, I mean, what I'm trying to stress is that the objects that the people would use in mathematics, like this guy, give you something that is kind of fake geometry. This is not real geometry in some sense, because this doesn't have any properties that you like out of a metric tensor, right? It's not positive definite. It depends, like this thing depends on the quadrant, so it knows about in fact, something interesting, I don't know what I do with this information. I don't do much, but maybe it is good information for you. This is a trilinear form, so this is a well-defined tensor in the good old way. So you can ask the typical question that one asks a tensor, right? Like, what are your symmetries? What are the transformations that preserve you? It turns out it's not too hard to prove, but it turns out that this thing has no symmetries. So you can permute the indices, obviously, and you can act with the identity. That's it. There's no linear transformation, invertible linear transformation that preserves this product, other the identity or basically reshuffling of indices. That to me is saying that the quote-unquote ternary geometry is not really speaking with our real geometry. So in some sense, it's not even geometry, this thing, but so what is it? Like it's something because it's there, mathematically it exists, but so I keep saying that it's almost like a conspiracy theory that you get to something that is simple, easy to define, but very hard to think about. So I completely agree with you with having geometry at this has been my intent from day one, is to find a manifold and say, okay, here a tangent space, I have this operation, and that's been like my thing from day one. But over and over again, I found that the natural things are sort of like pulling you away from the geometry that and it's uncomfortable. I don't know what other word to use. But yeah, any ideas will be welcome and happy to discuss. And you have my email probably somewhere, and you can contact me. One with this diagram, then the whole weirdness falls under this guy in the middle, because this object here, I mean, it sounds weird to say, but this object here is not very well understood mathematically. It's kind of some people, we are trying to defend that this should be called a triality, in analogy with a duality, where if you are in the binary case, delta ij is the matrix of the identity matrix, right? It's the component expression of the identity matrix, which some physicists might write as ij like that, so it corresponds to the dual pairing of covectors and vectors and whatnot. So if you try to think of what is the analog here, there's no mathematics invented for that. And it sounds very strange because it is that completely mundane object that all physicists are using every day, or most physicists, I guess, and that it appears in combinatorics all the time, and everyone is using these Kronecker symbols. But when you try and think about this as a multilinear object, it just happens that not much is known. The entire multilinear algebra of ternary operations is, again, very shaky ground. So I couldn't, I mean, maybe I don't know enough tensor network usage and theory to apply it properly, but as far as I could see, the burden was shuffled to the point that this is weird. I mean, none of my colleagues had ever seen like a three-wire joining in any of their applications. And then when we sort of disentangled it, we realized that actually that's just because this guy is very strange strange. It's a very naturally well-defined object, but not a lot is known about it. So that is not a very satisfactory answer, but that is where we are, more or less. But very good point. The tensor networks are definitely a way to approach. Oh yeah, so I can say something about Tija. So for better or worse, I only met him when he was very, very old already. So his mathematical intellect was in decline. So I managed to work with him on some more sort of philosophical problems. Of course, you might remember this news that he had solved the Riemann hypothesis and so on. Maybe I can. I think so. Yes, I think so. So his health was very delicate. He was an incredible human. What I can say is that he was an incredible human being. I mean, as a mathematician, I think he passed away 10 years ago, or by now maybe like 12 or 15 years ago. Everyone around him knew this. He was attending seminars. He was coming to, he was in one of my talks, and he was still there. He was very awake and you could hold a conversation about many things, politics and international relations. It was an amazing, human being. One anecdote was I was at that conference, and he said, "Oh, can you bring me like some juice or some coffee or something to drink?" I said, "Okay." So I went, grabbed the coffee, came back, and he was like sitting and surrounded by several young mathematicians. Everyone's like making connections about someone in Turkey and then someone in Brazil. It's like, this is an amazing human being, but he was just extremely well connected in Britain's politics, and from a very young age he was one of the scientific advisors in several campaigns against tobacco, against several things. I mean, he was an amazing, in the non-proliferation treaties, and he was involved in a lot of things. I mean, he was I remember when he died, we did a memorial service at the University of Edinburgh, and I gave a little speech there because I was honestly, I think my supervisor, myself, and his nurse were the last three people that he ever talked to, because I was going there every day or almost every day around that time. I would sit down with him and he would talk about how he thought that the quaternions would solve fundamental physics and had all these ideas. So for most of the time, he was given these very high-level, intellectually interesting conversations. And I have to say, talking to him about mathematics and physics was very, very interesting. But he could just not bring himself to doing mathematics as we know, which is, hardcore checking and proofs. And he was just very, very far away from that mentally. But as a speaker, as a human that communicates, he was very much alive, very much rich.
who's that?
This was before, I mean, this was after he died. Yes. I wish I could have asked about this because his insight, I'm sure, would have been interesting. I can tell you one funny anecdote just to end on a funny note. So some here know about Lie algebroids. Have you heard about Lie algebroids at some point? You have. Okay. So Lie algebroids. So it's algebroids. Yeah. So Lie algebroids are basically, the tangent bundle of a manifold. That's a Lie algebroid. That's one example of a Lie algebroid. So these are vector bundles that have a Lie algebra structure in the sections, basically. Anyway, the first historical example of a Lie algebroid that is not the tangent bundle, which is kind of trivial, is a construction in a paper from Atiyah from 1955 or something like that. When he works with group actions and the sort of the group invariant cohomology and all this stuff, he has a construction in that paper that in my field, which was this Poisson geometry that dealt with Lie algebroids, became very standard as the first non-trivial example of a Lie algebroid. So it is known as the Atiyah algebroid nowadays. Like you go to conferences and you say Atiyah algebroid and say, oh yeah, this is the M over G tangent. Yeah. So they know. Anyway, so the setting is we are invited in a guest lecture that he was inviting people from all his friends across the world, and he invites a geometer, and he's given a talk about two topics, and he decides not to reveal the second topic, and he gives the talk for the first half, and then has a blank slide, and he says, okay, I'm going to pass to the second half. And then Atiyah just stops him and says, okay, before you move on, I want to say something, because in the beginning, you have used this word algebroid and groupoid, and I'm very dissatisfied with this because, the word, why do we need this new word, algebroid? What is that weird word? So it basically gave this 5-minute rant about why the word algebroid is all wrong, you shouldn't use it. And then the speaker says, well, I guess you're not going to be happy with my next slide, and just clicks, and then there's Atiyah algebra. And you can't believe he was so mad. He says, oh, how do you do this to me? So it was very funny because he decided to give a 5-minute lecture on why the word algebroid was wrong, literally in the blank slide before the big title, the Atiyah algebra. So yeah, my supervisor and I always remember that moment because it was just priceless to be there. Yeah, so he was an amazing person. I mean, I have to say, unfortunately, I don't think I met Michael Atiyah, the mathematician. I think I didn't meet, but Michael Atiyah, the human intellectual, absolutely, and it was a privilege to meet him. So it's very nice. All right, well, thank you for your attention.